Okay, so good morning, welcome again to this new lecture on phase equilibria. So we are in 35th lecture today. So I'm just going to give you a brief recap of past lecture. So as far as recap is concerned, we started discussing about the ternary phase diagrams. Ternary phase diagrams are basically three-dimensional phase diagrams which have three components. So it could be three elements or three compounds which make binaries between each other. Like if you have ABC, three components, then you will have basically it's a mixture of three binaries AB, BC and AC, and these three binaries when they are put together, so you might have a situation like this. So this is first binary, this is second binary, on the back you have third binary. So you have A, B and C. So these are composition axis, and on the y axis you have temperature. And so you can have, for example, one phase diagram here. Let us say this is isomorphous between B and C. This is another isomorphous between, let us say, B and so this is isomorphous between A and B on the left. On the back you have isomorphous between B and C. On the front you have isomorphous between, let us say, between A and C. And on the top of it you will have a surface which is so this surface on the top, this is the liquidus surface, okay, whereas at the bottom you have this one. If you connect these together, this is the solidus surface. So you have three-dimensional surface. So you have a surface basically giving you, it's a contoured curved surface which will be a liquidus, and in a similar fashion at lower temperatures you will have another surface which will be curved in this fashion, and that will be solidus. I mean, they may also touch each other somewhere in between, either giving you a maxima or minima depending upon the phase diagram, but for a simple isomorphous system you may have one surface, one curved surface giving you liquidus, another curved surface will give you solidus. So this will be liquidus and the one here will be solidus. So it's a three-dimensional phase diagram, a ternary system, and basically you draw it in the fashion of equilateral triangles. We saw how to determine the composition. So for that we saw that if you have ABC, then if you draw a horizontal line to BC, then this line will give you composition of A. Similarly, if you draw a horizontal line parallel to AB, it will give you composition of C. Similarly, if you draw a horizontal line parallel to AC, it will give you composition of B. And remember, XA plus XB plus XC should be equal to 1. There is another method that can be drawn as, that is the altitude method, which means altitude of a equilateral triangle. So if you have a altitude, you can take the altitude, for example, this is the altitude, and this altitude is sum of this, that and another. So these are three altitudes which you can take to be so these three altitudes will be equal to the overall altitude of the equilateral triangle, and they will also represent compositions. So nevertheless, XA plus XB plus XC must be equal to 1. So the corners represent the pure materials, the sides represent the binary systems, and somewhere anywhere in between the triangle you have a ternary system. So and we looked at basically we are looking at certain rules. The first rule that we looked was if you take a line, for instance, here in this case, and if I draw a line like this, and let us say if this is ABC, then along this line the composition of A remains, the fraction of B and C remains the same, You can vary the composition of A along this line, but so as you move farther away, you will decrease the amount of A, but the ratio of B and C remains the same. So that was the first thing that we discussed. Then we discussed that if you have this line, for example, if you draw another line like this, then since this line is parallel to BC along this line, the if you move the alloy along this line anywhere, you will change the proportion of B and C, but you will maintain the constant amount of A. And then we looked at the third rule, that was the lever rule. And so if you have so this is for instance A, B and C, and if you mix two alloys, let us say A and B, then the third alloy which forms as a result of the resulting alloy, let us say C, falls on a tie line which joins A and B. So it is a straight line joining A and B. In between, depending upon the proportion of A and B, you will have C lying, and this percentage of, for example, your B phase will be equal to AC divided by AB into 100, and percentage of A will be equal to BC divided by AB into 100. So this is nothing but lever rule that we saw in practice. All right. Now let us move on to another few more aspects. So we will first go to rule number 4. The rule number 4 says that if you have 3 alloy, if one mixes 3 alloys, let us say X, Y, Z together, the composition of the resulting mixture will be at, let us say in this case, so if I draw a triangle this fashion, okay. So this is the projection that you have, and let us say you have a alloy X, somewhere you have Y and somewhere you have Z, and if you mix them together, you form you make a triangle by connecting these two, and the alloy that forms, let us say, lies somewhere here. Let us say this is the point T, such that, so when you draw, let us say, projections, so this is, let us say, X prime, this is Y prime, and this is Z prime. So basically the resultant alloy, the composition of the resultant mixture will be at a point, let us say T, in a triangle X, Y, Z, formed by joining the compositions of the alloys, okay, and you draw the straight lines, they are not curved lines. So it is as if it is at the center of the gravity. So it is like point fulcrum at you have a body whose fulcrum lies at T, and it has some mass attached at its corners like X, Y, Z, and which basically represent the alloy compositions. So under equilibrium conditions, the percentage X is equal to X1 T divided by X1 into 100. Similarly, percentage Y is equal to Y1 T divided by Y1 into 100, and percentage Z is equal to Z1 T divided by Z Z1 into 100. So, this is all coming from basically properties of the triangles. So, generally in by ternary system, we do not look at the 3D diagram. We are mainly looking at various sections, isothermal sections, vertical sections, and so on and so forth. And when you put these sections together, so you can have a if you draw a ternary phase diagram, for example, like this. Okay. So, the sections could be, horizontal section like this. So, this would be isothermal section, because you have T here and ABCs are here. So, this is the isothermal section. You can have vertical section. So, for example, you can have a section like this. This is the vertical section. You can have another vertical section like this, for instance. So, there are various vertical sections which are possible. So, if you, by looking at these various sections, you can understand ternary diagrams a little better. So, so these sections are, for instance, you can have Liquidus plots. Now, Liquidus plots, as I just explained to you. So, if you draw, let us say, a ternary phase diagram, right. So, you have okay. So, let us say one part of the phase diagram is this. So, this is, let us say, A, B and C. Another part of the phase diagram is something like this, and this is the BC part of the phase diagram, which is like this, right. So, you can see that this is Liquidus, this is Liquidus, this is Liquidus, and this is Solidus, Solidus, Solidus. Okay. When you connect Liquidus together, so this surface, the top surface, consisting of Liquidus. So, this surface on the top, this will be essentially the Liquidus surface. This Liquidus can be projected onto a surface. So, for example, if you have a system such as the one which I am going to draw, with little complex. So, let us say a surface like this. So, basically what you can do is that this surface can be represented by, let us say, these lines. These lines are nothing but constant temperature lines. So, you draw constant temperature lines on this surface. So, generally it will start from one end. So, when you draw these constant temperature lines, you can project them in 2D. So, and these would be the, for example, lines. So, depending upon the melting points. So, let us say if C has the highest melting point and B has the lowest melting point. So, this would be T1, T2, T3, T4, T5, T6, T7, T8, T9, T10, T11. So, this is basically by picking up the constant temperature lines on the surface, you are projecting them on the 2D plane. So, this is what is a Liquidus plot. So, it allows you to visualize the Liquidus. Similarly, you can draw a section at you can do the Solidus, you can do the same for the Solidus as well. So, you can have a Liquidus plot like this, you can have a complex phase diagram. For example, let me draw a little bit longer lines here. So, let us say we have a phase diagram which is let me see. So, if you have okay, and let us say this touches somewhere here. So, you have a similarly for this side you can draw another eutectic phase diagram. So, okay. Similarly, on this side you can draw another phase diagram, which is this is the eutectic. So, connect this line. So, let us say so. So, these are the corners are A, B and C, and you see three ternary diagrams, one between AB, second between BC and third between AC. Now, on this ternary diagram, if I connect the points lying, so this is these are the melting points of A, B and C, and if I connect only the liquidus lines, so this is liquidus, use this color liquidus. Let me use different color. So, this is liquidus, this is liquidus, this is liquidus, this is liquidus and this is liquidus, and these eutectics will meet somewhere here, okay, and this will form, let us say, a ternary eutectic. So, this surface which is shown on the top is essentially the surface that represents the liquidus surface of a ternary eutectic. So, on this you can draw constant temperature contours, and when you project them in 2D, so let us say this is ABC eutectic thing. So, now you can start. So, this has, so in the previous case it was like this, there was no nothing very complicated there, you just draw the constant temperature lines on a 2D diagram and they just show the temperature profile. So, this is the profile of the surface. In this case, since you have a ternary eutectic somewhere in the middle, there is a dip in the middle. So, what happens is that you draw the isothermal lines. So, they say this is how you draw, and that is how they start merging into each other. So, somewhere in between you will have a eutectic somewhere. So, these lines they basically merge towards each other to form let us say eutectic. Okay. So, various lines merge towards to form give you a eutectic. So, this is so for the sake of it, let us say this is 400, 300, 200, this could be for example 500, 400, 350, 300 and 200, or this could be for example 650, 500, 550, 400, 200 and so, and this will be the, so all the three lines merge to the contours merge to give rise to a ternary eutectic point somewhere in the middle. Draw it slightly more clearly basically. So, you have, so essentially you have the temperature lines coming from A side, temperature lines coming from the C side, temperature lines coming from the B side, the contours, and these contours merge together somewhere in the center to give you a ternary eutectic point. So, this is how your liquidus of a ternary eutectic will. So, this is percentage A, percentage B, on this you will have percentage C, this will be percentage A. So, this is basically useful to determine, for example, the freezing point of the alloy. So, you can see that if the eutectic falls here, you know that this is the minimum temperature that you will have in a ternary eutectic system, and this is the minimum freezing point of the alloy. And this also helps in identifying the primary phases that form during solidification in a ternary alloy at a given. Okay. So, the next thing that we do is to basically look at the isothermal plots. Okay. Basically, these are plots drawn at constant temperature. Okay. So, and these are useful for predicting various phases, useful to determine the phase and their amounts, compositions, etc. Okay. So, you can have, for instance, situation like this, in which, so if I take a cross section in the previous diagram at a lower temperature, so in this, let us say if I take a diagram somewhere at this point, so let us say this is the T1, then what I will see is that if I project it in 2D, yes, if I take it in 2D, what I see is that, so this is A, B and C. So, you can have a line of A something like this, line of B something like this, and line of C something like this. So, this would be, for example, gamma phase field, this would be beta phase field, this will be alpha phase field. Between these two you will have alpha plus beta, alpha plus gamma, beta plus gamma, and then you will have alpha plus beta plus gamma, the three phase field, and hence, and you can vary the compositions in this direction. So, this would be A, this would be C, this would be A, this would be B, C, this would be B. Okay. So, this is how you draw the isothermal plots. So, they are drawn at a constant temperature, taking a section, and this allows you to determine. So, for example, if you draw in an isomorphous system at low temperature, you will see only alpha phase. So, this is isomorphous, completely miscible system. If you go to high temperature, you will see only liquid. At lower temperatures, you might see liquid and solid. So, that depends, all right. So, these are isothermal plots, and then we determine another thing which is called as isoplets. Isoplets are basically vertical sections which depict phases at various temperature. Okay. So, for example, if you have again, if I go, so if I draw now let us say a simple phase diagram . Okay, and let us say okay. So, this is A, B, C. So, you have liquid, this is liquid plus solid, liquid plus solid, and liquid plus solid. Here you have solid, and on top you have liquid. So, let us say if I draw a section which is something like that. Okay, so right through. So, essentially I create a vertical line like this, and then I take a section which is parallel. So, let us say I take a section like this. So, I can see that this is the section that I am drawing, all right. And you can see that if you now project this in 2D, so you can see that you are going. So, this is a section, you started from pure B and you have gone to some A by C ratio, okay, some A by C ratio, and you can see the phase field varies. So, as this is the temperature axis, you can see that somewhere here you have starting from liquid plus solid, and then you go to this regime. So, you have a phase diagram which shows the liquid, the liquid plus solid. You might have a situation in which something like this, let us say. So, you have, sorry, not very neat. So, you may have a situation something like, so in this phase you have, so you have completely solid regime here, something like that. So, you have liquid plus solid, then you have solid. So, something like this you may encounter. If you want to see something in the binary phase diagram, it may appear, let us say, something like this. So, you have, let us say, A some let us say 30% of C, and this point is B 40% of C. So, let us say if we go to section in this diagram, okay. So, we go through a section like this, okay. So, this is the section, and if you raise this section, take a vertical section and draw it. If you take a vertical section and draw it, you might see something like this. So, let us say you have a alpha, so something like this, let us say. So, the phase boundaries may not actually, in these things, isoplets are not actually phase diagrams, they are not complete phase diagrams, they are only sections. So, as a result, you will see phase boundaries doing all sorts of funny things. They may not complete the, so this is L plus beta, L plus beta plus gamma, this is beta plus gamma, this is alpha plus beta plus gamma, this is, let us say, L plus alpha, this is L plus alpha plus gamma, and this is alpha plus gamma. So, you can see this is the vertical section starting from A alloy containing A 30% of C and B 40% of C, and this is how it will vary, and somewhere in between it will have certain composition which shows a minimum point transforming from liquid. So, this is the eutectic composition of ternary, showing you a minimum melting point. So, these are the isoplets which basically depict the change in phase type as the temperature changes for a fixed A and B ratio. So, these are certain characteristics of ternary phase diagrams that we have discussed. These characteristics allow you to depict ternary phase diagrams and imagine phase diagrams in a better sense and a better way, and they allow you to study the microstructure evolution phases, their compositions, etc., in a more meaningful manner. So, we will do further discussion on ternary phase diagrams in the next lecture. Thank you.